Okay, thanks a lot for the invitation. So indeed, I'm going to talk about this topic. So the goal of the talk is survey some of the outcomes of this famous proposal of Kapustin and Witten, and then say something about stringy perspective. So it consists of two parts, QFT and geometric representation theory, and then string theory and GRT. And my understanding is that the audience is quite broad. I'm not going to be too technical. I will try to suppress some technical aspects, which for me, like main technical aspects involve what is called the derived algebra geometry. It's a little too technical, so I'm not going to use that. And BB formalism, I'm going to sort of use that, but not really going to explain. I'm going to try to explain things in words. Okay, so let me start from the beginning. So I want to explain sort of how quantum field theory has been used for mathematics in some examples. So for that, I want to start with an introduction, which is that what is QFT? And QFT, at least at its first approximation, is given by studying this integral of this particular form. And here, this E is just a space, and this define is a volume element, and there are just functions, and you're just thinking of such integrals. And the simplest case you can think of is maybe E is just a real number with the usual measure and polynomial function. Then the thing you're interested in is just computation of such integrals, which is a topic of calculus. But of course, that's not the end of the story, and it's hardly a beginning, because usually, in fact, you need to consider a particular form of E and S and OI. So for that, the input data, I want to say, is starting with space-time, which is just, mathematically speaking, just a smooth manifold, M. Another data is you have a fiber bundle, and you think of sections of such a fiber bundle, and that is called the space of fields of your field theory. Next thing, you consider functional on your space of fields. So these are the input data, and somehow you care about this outcome, which are called the correlation function. And somehow, these play a really important role in, of course, in physics and also in mathematics. And I just want to give a name, like if the space-time is d-dimensional, then it is called the d-dimensional QFT. Okay, so let me see some examples. These are essentially the most famous examples, at least for when it comes to, as far as applications of mathematics is concerned. So I just brought three examples, one in 2D, one in 3D, one in 4D. So accordingly, your space-time is two-dimensional manifold, three manifold, four manifold. And as I said, you need to fix an input data. So as an input data, you need to think of some sort of sections of a bundle. And in the 2D case, you think of maps. In 3D case, you consider connections, which you may either think of as one form. And in this 4D case, you also think of the G connections. And you cannot just write down action functional. And this is sort of the, these names actually determine what kind of space of fields you consider and what kind of function you consider. And you can just write down. It's not important to sort of know what they are for the purpose of space stuff. Plain is you can just write it down, given this name. But the point is that for mathematics, before thinking of these sorts of physical input data, there was a pure math subject, like universal geometry, knot theory, and four-manifold theory. And somehow, by the work of these people and others, you now, and using this idea of field theory, and in particular correlation functions of fluid field theory, you now understand things better. And it's actually enhanced to, in a sense, like different subjects. So universal geometry is, part of universal geometry just becomes a part of neurogeometry, which is a new topic. Also, quantum topology is just born out of such a thing, Chern-Simons theory. And also, side Witten theory, it just has revolutionized like whatever the smooth four-manifold theory. So such a thing is a well-known history by now. One thing I want to note is that all these cases, which are, again, like claim, essentially the most important, historically speaking, applications to mathematics as of yet, they all depend on the topology of your space-time manifold M. So that's why it's called the topological QFT or TQFT. And you may wonder, then what if we consider more general QFT? Like, doesn't it have like even more information? Isn't it like even more fun? That should be true in a sense. On the other hand, somehow in mathematics, we want a little more structured data. Like all these things are kind of structured things. And to get these sorts of things, it seems it is important to have cut down some information and actually consider TQFT. Okay, now I want to talk a little bit about geometry-Langlands. So geometry-Langlands is study of some objects you consider you can attach to such a pair, where the pair consists of a Riemann surface and a complex league like GLN. And what is usually called the geometry-Langlands correspondence is an equivalence of two categories. And I'll say a little more about that soon. And the story for today is that it actually starts with this work of Kapustin and Witten, which is that they found a physical context, just like what I showed in the previous slides, for a version of geometry-Langlands correspondence, again in terms of 4D TQFT. And here, the important thing is that 4D TQFT, when I say that, the important thing is that your space-time manifold is four-manifold. You just need to kind of specify what kind of four-manifold you consider. And I'm saying that the C, which you are using in geometry-Langlands, to formulate geometry-Langlands, is used in your space-time. Your space-time is four-manifold. Riemann surface accounts for two-manifold, and you have another kind of two-manifold sigma. So that's how you have 4. 2 plus 2 is 4, right? So by thinking of particular four-dimensional TQFT on a space-time of this particular form, they found a physical context. But one thing I want to point out here is that this Riemann surface is, this is a Riemann surface or algebraic curve. So just topologically, that means that it does depend on the complex or algebraic structure of your space-time. Whereas if you actually think of TQFT, it is TQFT, like a topological quantum field theory, meaning it depends on the topology of your space-time. It essentially depends only on the topology of your space-time. So whatever the proposal you may consider out of this, it's just not going to capture sort of the subtle part of the Langlands theory. So for example, like if you think of, let's say when C is an elliptic curve, there is like a 4 moduli of elliptic curves, right? You may have usual kind of a picture of fundamental domain and so on. And for each point, we have different statement of geometry-Langlands. But somehow, if you're thinking in terms of TQFT, all the elliptic curves are the same. They are just torus. So in that sense, TQFT just cannot really capture this geometry-Langlands. And that's also big reason why geometry-Langlands experts haven't sort of paid too much attention to the work of Kapustin and Witten and tried not too hard to understand their work. But this is kind of the fundamental problem because it is important to actually consider TQFT to see anything like geometry-Langlands from physics perspective. Okay, so that was sort of the background. And let me start with introducing geometry-Langlands. As I said, as an input data, I start with its thing, Riemann surface and a group. And this involves the Langlands duality, so there is something called the Langlands zero group, but it doesn't really matter for this stuff. You may just consider whenever you see G and G check, it's all GLN. That's totally fine. And this particular form of geometry Lagrange was formulated by Bellinson and Greenfeld in the 90s. It says there is an equivalence of two categories. It goes like this. It's called the best of conjecture. The best of conjecture says that there is an equivalence of categories between these two things. So let me read them off for you. The left-hand side, this bond G, this is just a moduli space of G bundles on C. And D module, it just means the category of D module. And flat G check of C, the moduli space of G check flat connections on C. And then you are thinking of a category of quadratic range. So I mean, I don't suppose everyone is kind of familiar and just understand what's going on. It's just maybe words. Let me say a few more words. So a way to sort of maybe understand or remember this thing as a mnemonic is that, you think of bundle here, but what is the D module? D module is just essentially a bundle with a connection. So in that sense, the left-hand side, you may want to read it as on the space of bundles, you think of category of bundles with flat connections. So in that sense, the left-hand side is category of bundles with flat connections on space of bundles. And on the other hand, on the right-hand side, you have flat bundles, and you think of quadratic range. So then you may want to read it as a category of bundles on space of bundles with a flat connection. So there is some fundamental asymmetry. The flat is moving from here to there. And that's somehow showing some feature of geometry Lagrange correspondence. There is fundamental asymmetry right there. And this is the point that I was basically saying. So if you are not careful about these sorts of things before, you may not know this, but space of local system and space of flat connections are not isomorphic, at least in terms of algebraic symmetry, which is sort of the realm of geometry Lagrange. So that's that. And another thing I want to say is that I stated this as a meta conjecture as opposed to conjecture, and that is because the conjecture is known to be false as soon as just this is non-abelian. And there is a version of a corrected version by Arrington and Gaiswood. And it is basically being proved like last year and this year. So I think you may have heard the talk last week, and you may be hearing another talk tomorrow about the proof. Okay, so as I said, and I want to emphasize once again, the second part is the part I emphasized in the previous slide, which is that in terms of the usual physics framework, I mean, if you ask the physicist, or if you are a physicist, think of the space of local system, space of flat connections. You don't really have a way to distinguish them. They are just the same, right? But somehow, for the purpose of geometry Lagrange, you don't want them to be the same. Like they are just different. For instance, this modulus local systems as an algebraic object does not depend on the complex structure of C, whereas this flat G check of C does. So they are just completely different, at least for an algebraic matter. And there is just no framework of physics to have that into account. Okay, so given that, I want to just explain. So this is the technical slide, and after that, I'm going to become less technical once again. So one of my early works is to develop a framework of such a sort of field theory, to deal with such things. And for that, I was using what is called the derived algebraic geometry. And the reason why this was essential, the derived algebraic geometry was essential, was that this topic of derived algebraic geometry is, in a sense, by definition, does have topology, usual kind of homotopy theory, and usual algebraic geometry in it. So both of them are living in the same category, so that you can actually kind of deal with both things under the same roof. So that's a hint that maybe if you want to develop a framework of physics which can cover geometry Lagrange per se, this is sort of the right direction. But then you ask, if you think about, at the end of the day, this Kapustin and Witten did consider topological field theory. And again, for the experts in the audience, topological field theory in this sense is realized as doing a topological twist. And thinking of what it is, you are thinking of situation where your translations are acting in a trivial manner. And how can it be not topological with that input? And that is precisely captured by the definition of what is called the drum stack. I mean, that is also part of something you can consider in usual algebraic geometry and also in derived algebraic geometry. So again, what I'm saying is that from physics, you know that the translations must be acting in a trivial manner. And that kind of information is captured by having what is called the drum stack. And if you remember, I had a mnemonic, which is about category of bundles on like flat bundles and category of flat bundles on like bundles, whatever, these sorts of things. And this fundamental of symmetry can be, oh, sorry, I missed the B here. So supposed to be classifying space, BG and BG check. And this is a mapping space. So by definition, mapping space from C to BG is what is called the bond G. And yes. So anyway, it's having drum here and there. These are exactly sort of the responsible for this having fundamental asymmetry or having flat here or there. And again, kind of the I mentioned in the second point, this what is called the log G and flat G, they are different. Their difference can also be captured by the notions in derived geometry. What I denote by flat G is, oh, sorry, there is another paper, this is G check, and B. Flat G check is mapping space from the drum stack, and this B is short for Berry. You're thinking of Berry stack, and if you're thinking of mapping space from the Berry stack, that's what is giving you a local systems. So they are different objects, as I said. This depends basically only on the topology of C, and this does remember actually the algebra structure. Still keeping the information of somehow the locally is trivial. So kind of the infinitesimally trivial. Right, and I didn't quite write it here, but using this, you can actually obtain what is usually considered in geometry Langlands correspondence at the level of what is called the derived stacks. And the second paper on the topic, we discussed the notion of moduli of vacua and quantization in this framework. So somehow, if you want to get to whatever application of mathematics which does involve algebraic geometry at the level of space-time, you need to, there are some ideas from physics, but you need to do it again in this new framework. So we had to do some of them. And although I didn't sort of say anything about this work of Arlington Gaisry, there is a modification, and I'm claiming that there is a way to obtain such a modified conjecture starting from physics. So this was not known even in terms of physics before. And it's basically kind of, as always in this interaction between mathematics and physics, once you find some new context or the right physical context for mathematical statement, you can expect to obtain some interesting results. And that was actually the case. You obtain new conjectures and prove special cases. So the conjecture is kind of surprising nature. Depends on sort of the, again, choice of C and G. And sort of with Chris Elliott, we proved the conjecture when C is P1. And Arrington told me that like his work, unpublished work with gauge free amounts to the conjecture when G is SL2. So it seems like it's a true statement. It's interesting, but somehow to state that that's just too much for, I think, for this time. So maybe kind of the important thing to note is that these sorts of things, our work actually does have interpretation in terms of string theory as well. It does play an important role, but somehow explaining that, again, takes us too far afield, but so let me not. Because this was a little too technical, let me just explain what kind of thing we did, just as an analogy. I mean, if you think about the famous story about the four manifold theory, where Donaldson did a pioneering work, you just kind of find this nice invariance of four manifold by thinking of this instant moduli and so on. But somehow Witten in 88 found physical context, and this is kind of how or why he introduced this notion of topological quantum field theory. But then, in order to get to finding some kind of the mathematical application, like to the extent that like mathematicians can appreciate, you need to do something. You need to develop like physics also further, right? And that was an important work was done by Witten. And then using such an idea, Witten was able to write down this Seiberg-Witten equation, what is called the Seiberg-Witten equation, and that just changed the field ever since. And there is an analogy. In the field of geometry Langlands, Berlin and Drinfeld made this pioneering work based on other work, making this conjecture, for example, and so on. And Kapustin and Witten kind of provided a first shot at this physical context, but that wasn't quite for the version of geometry Langlands that Berlin and Drinfeld formulated, as I explained. It's kind of a topological version thereof. So we needed to find sort of the physical context, or rather, like new framer to accommodate such a thing, and then needed to develop some more of physics thing, which is about this modular vector. And then using that, we were able to find some new mathematical results as well. Right. So there are some other developments, and there are several different versions of Langlands duality that's around. Famous ones include Fagan-Frankel duality and fundamental local equivalence and so on. And I found a physical interpretation of these things, and somehow they are used by Frankel and Gayotto extending what is called the quantum geometry Langlands, and also in other work used to formulate what is called the Gayotto conjectures. Again, you may have heard a talk on this topic by Sasha Braverman last week. And somehow, to formulate the conjecture, this physical interpretation was used. Also, I should say that Gayotto sort of independently developed his own approach to understanding or extending geometry Langlands, mostly based on sort of vertical algebra. That's another important direction. For mathematics of geometry Langlands as formulated by Berlin and Drinfeld, motivated by the work of Kapustin and Witten. But I should also mention there's another direction, which is pretty exciting. Bensby and Nedler developed what is called the Berry geometry Langlands. So, and this one is taking this perspective of PQFT much more seriously. So remember, the geometry Langlands, and at least like until like recently, when you say geometry Langlands, it just means what's formulated by Berlin and Drinfeld. But Kapustin and Witten kind of said that like there is something like geometry Langlands if you think of this kind of the PQFT. So I, with collaborator, thought that there must be physics framework to do geometry Langlands per se. But Bensby and Nedler thought, given the same kind of the input data, thought differently. Maybe there is a version of geometry Langlands it's more like what Kapustin and Witten said. And that's kind of the Berry Langley. If you remember, I considered the drum stack and Berry stack, and thinking of Berry stack kind of the based on Langley's based on such a thing is called the Berry Langley, and this also has recently been proven to be pretty useful in understanding the other forms of Langley as well. So quite exciting stuff coming out of this proposal of Langley. Okay. Another thing I want to say is that, like Witten introduced this PQFT for manifolds, in particular this notion of topological trees. But once you introduce that, then you can apply this procedure to like a lot of supersymmetric theories. So like mirror symmetry is also one example coming out of that. So same here, because we kind of build this framework, we just wanted to apply this to. I just wanted to apply this to sort of other field theories, and just one example is symplectic duality. Oh, I think I messed up slides a little bit. These were, Bullimore, Timofte, Ayoto, Hilburn, and Brabman, Hilburn, Nakajima. So they kind of did work relating this symplectic duality and three-dimensional four theory, and we did this work on. So as you can imagine, this red is physics work, blue is like mathematical work. We did this work. But there was another work by Ayoto Witten relating this three-dimensional four theory and four-dimensional four case theory. And with Justin Hilburn, I developed somehow like mathematical counterpart here, which actually from this we are connecting these two different fields. So Brabman, Hilburn, Nakajima has a sort of famous construction called the Coulomb branch. So we did construct a category, monoidal category, such that if you think of endomorphism algebra of the unit object, that's recovering Coulomb branch construction. So it is categorification in that sense. And it's kind of hard to explain sort of the relation, but they are related, and we found some new relation. And this new relation was, at least the simplest case, was proven by Justin Hilburn and Sam Reskin. Another exciting development I should mention is that Benzibi circularity Venkatesh kind of applied same physics work to a more arithmetic setting, and then somehow as a result, they obtained what is nowadays called the relative Langlands program. Okay, so that was the first part of the talk, QFT and GRT. Now the second part. So somehow the motivation for the second part for me was the following. So I developed some kind of framework for physics and tried to understand it better and so on, but I was basically never sort of fully satisfied in the sense that I didn't quite understand what S-duality means. So I needed to sort of so we are trying to maybe say conjecture and prove things that the two things are equivalent, but which two things are equivalent? Like I have no sort of intrinsic idea of how it works. I just had to believe like what physicists say. So I wasn't really happy. So that's why I wanted to understand this duality itself a little better. So for that, of course, the question would be, what is S-duality? And one thing physicists would say is that S-duality is something that's easily seen in the context of string theory. And they would say that there is this diagram where this M stands for M theory. So this means that you think of M theory on circle times 9 manifold. You may have heard somewhere that M theory is 11-dimensional theory. That 11 checks out here, 1 plus 1 plus 9. That 11 is this 11. And this 2A is what is called type 2A theory, type 2A structuring theory. Again, string theories are 10-dimensional, and 1 plus 9 is 10. And this reduction map is an equivalence. I mean, physicists would say that whenever you have this circle on M theory, and if you reduce along that S1, they should be equivalent. There's another thing, also for T-duality, between type 2A and type 2B, like this. It's also an equivalence of string theory. But with this prepared, I can say a little more about this S-duality, because I have this S1 times S1. SL2Z is just acting just on this S1 times S1. And because these are our equivalences, this action of SL2Z on M theory, you should be able to transfer that further down to this 2B. And this is one way physicists would say like what an S-duality is. So basically the idea is that, I mean, string theory is like not quite defined in any reasonable sense. I mean, mathematically it's just like impossible at the moment, and even physically it's really kind of hard to understand. So basically the strategy would be try to understand a version of this statement to make sense of S-duality. And we just want to understand a part of what is called S-duality. And that will be, we want that to be enough to give some results to mathematics. And after all, like we are thinking of some TQFT or something like that, we already lost a lot of information, and that was enough to give exciting results to mathematics. So maybe even in the context of string theory, you may lose a lot of information, but they may be okay. That's the hope. So for that, let me start with saying a little bit about type 2B string theory. So I cannot really say much about it, but let me just say a few words about like what kind of things are there. Again, these are just like words. You shouldn't really be afraid. And goal is to explain a little bit about these things and how things are put together to explain something about mathematical structure. So physicists would say that there is something called the D-brain gauge theory for the 2K minus 1 brains. I mean, these numbers actually depend on sort of the fact that we are thinking of 2B string theory. But 2K minus 1 brains, whenever you see this, you are thinking of 2K dimensional submanifold of your given 10-dimensional manifold, space-time manifold. And somehow, whenever you fix such a submanifold, effectively speaking, like somehow you are ending up with some 2K dimensional field theory. Remember, field theory dimension was counted by sort of the dimension of this space-time manifold. So D-brain gauge theory is another field theory you can construct automatically just by thinking of submanifolds of your big 10-dimensional manifold of string theory. And just as an example, when you say these 3 brains, when people say these 3 brains, that should be on a 4-dimensional thing. So the simplest case would be to think of R4 sitting inside of R10, and that is giving what is called the 4D and equal 4D. Again, names are not so important for today, but these are to speak perfect. The 5 brains gives a 6D theory. Another thing that plays a role for us is that what is called the closed string field theory. This is a field theory, but it is maybe a little confusing because I didn't quite explain much about things. But string theory is, when I say string theory on 10 manifold, the input data to actually consider such a thing involves some like Riemann circuits and so on. You're thinking of some sort of 2-dimensional theory, target 10-dimensional manifold, but somehow you're doing a lot of different things. On the other hand, when I say closed string field theory, the idea is that you think of a field theory field theory in the usual sense, to a large extent, living on 10 manifold, and it must be having same amount of information of this 10 manifold, the usual string. That's the idea of string field theory. So it's a string theory, but then in terms of field theory, so that's why it's called string field theory. And another important thing I should mention is that closed string field, closed string state, which is an element of closed string field theory, is supposed to yield the deformation of D brane gauge theory. And as I mentioned in the previous slide, this type 2B string theory, whatever it is, it does admit SL2Z symmetry, also known as S-duality. So, as I said, like somehow these are important data, but we have like no idea what they are. So mathematically, we want to understand. So the answer is that this can be understood not like directly, but after some twist. The twist, sort of in the sense of like topological twist. So if you know what I mean, it's a smaller part of string theory for which I can understand all these things in a sort of rather rigorous manner. That's the claim. So let me try to explain what these things are. Now, that's going to take, I guess, some 10, 15 minutes. For that, I want to actually kind of digress and explain the usual TKFT. I mean, when mathematicians say TKFT, chances are they are actually thinking of this definition, not the sort of physicist TKFT. This is what is called the functorial TKFT. So TKFT is a functor. I am actually kind of assuming that people have seen it. So I'm just kind of leaving it out here just for notation. A symmetric modular functor from this Boltzmann category to vector space category. And two-dimensional TKFT is determined by cumulative Frobenius algebra. Because, you know, here you have all these morphisms and they are going to correspond to this, and somehow the compatibility you have on these morphisms, that's restricting your how your morphisms to behave, and that's giving the axiom of cumulative Frobenius algebra. That's the claim. But one thing I want to emphasize is that physically, this what you assign to S1, so ZS1, which I denote A, physically that has an interpretation of the space of closed string states. And then the natural question is, what about an open string? Like meaning an inner verb for us. So closed string, because it's like a circle, which is like really closed string. And inner verb is an open string. So to understand that, I think it's mathematically kind of the best way is introduce what is called extended to-D TKFT. The claim is that it's essentially sort of looks almost the same, but you go a little deeper. So before you're thinking of a category, you have just thinking of these two rows, but now you go all the way down. You think of zero manifold and voltage in between zero manifold as well. And then it's going to make a two category. So the target should also be a two category. So it's essentially a category of category. And for technical reason, I'm thinking of what is called the DG categories. What is known as a theorem in this context is a classification result. It says that such an extended to the TKFT is determined by what is called the Calabi-Yau category, which is what you assign to a point. So in the previous slide, your usual 2D TKFT was determined by what you assign to S1. But now it's even more local. I mean, the locality of physics is essentially the reason why this works out. What you assign to point does know everything. Somehow, if you know the point, you can just kind of, in a sense, integrate out to like any sort of the two manifold to obtain everything. And in fact, this theorem itself, I mean, this much is actually due to like Kevin Costello and a version due to Hopkins-Lurie, but even for general dimension, this works, and that's a result of Lurie for the cobordism hypothesis. And once you have that, then it does give an answer to our question in the previous slide, because it gives an interpretation. So what you assign to a point, which is a category, this Calabi-Yau category, that is kind of the what is called the category of boundary conditions. And if you pick two boundary conditions, B1 and B2, then this Hom space, these are the inner birds, namely open string states, which does satisfy fixed boundary conditions B1 and B2 at its ends. Okay, so now using these sorts of things, I want to explain this ingredients of the string theory. And for practical string theory, at least for today's stuff, I'm thinking of some Calabi-Yau category. I mean, there is notion of dimension. And I'm going to maybe explain this in examples. So the example of Calabi-Yau 5 category is that given, consider some Calabi-Yau 5 form, you think of the usual sort of the thing you would consider in the context of mirror symmetry, like Mukai category of this X, or derived category of coherent case on X. And as you know, as I claimed, whatever these things are, they just do determine everything of your field theory, in particular what you assign to S1 as well. And abstractly, you know that that's actually going to be what's called Hochschild homology. And computing Hochschild homology of Mukai category of coherent shifts, the quantum cohomology and polyvector fields respectively. Polyvector fields play much more important role for us. So I'm actually kind of defining here. This is direct sum, has a direct sum decomposition PVIJ, and PVIJ just looks like this. And the usual kind of the exterior power of the holomorphic tangent bundle with the anti-holomorphic direction, and it has a the bar operator as well. And because it is assumed to be Calabi-Yau, the D operator on the this smooth forms can be transferred to define another operator D, which is also the polyvector fields. These are technical points, not too important. So my claim was that what's in this box. So type 2B string theory, if physicists say this to you, mathematician, you guys just may think of Calabi-Yau 5 category. That's kind of what I'm claiming. For the most part, at least, I mean, there is no way you can understand this 2B string theory anyway as a mathematician. So, but if you think of Calabi-Yau 5 category, thinking of the Calabi-Yau 5 core, or thinking of this category, these are good enough approximations to understand, get some sense of what kind of things they are thinking of. Sorry? M10 is what? Not, I mean, doesn't really matter for this stuff. Yeah. This kind of formal procedure that doesn't really matter. So I need to say a little more to be precise about Calabi-Yau in that case. So if you want, you can just assume compact proper. But the formalism works out even if it's not assumed. Like this, the cotangent model of the smooth domain. So thinking of some Calabi-Yau 5 for or this form, that they are all giving examples of Calabi-Yau 5 category. And again, these are models for type 2B string theory. Another thing I mentioned is what is the D brane gauge theory. And physicists would say this T is for physics, I guess. Open strings ending on branes D is D brane gauge. That's what they would say. But if you think about, if you understood the interpretation I was giving for open string states, and the morphism of B just is open strings with boundary conditions satisfied like with D at each end. So what physicists would say is just translated into this thing. If you think of the endomorphism algebra, that's describing your deep brain gauge theory. So that's another translation. And this technical part, somehow the assumption that I was making that DG category, Clavic category, these do give the necessary structure here to understand this as a field theory, this kind of abstract thing. In example, so in the previous slide, I was thinking of this particular Clavier 5 category. You think of the D3 brains, which is again kind of 4 manifold, thinking of C2, and here R2 times C, like this. And you can just compute this self-endomorphism to obtain something. And if you're a physicist, of course, you should expect 4D equal 4 theory. But I'm claiming that if you just compute this is a result which you may not recognize, but the claim is that you obtain certain twists of 4D equals 4. So because you started with a certain sector, subsector, or subquotient sector of your string theory, the resulting D-brain gauge theory should also be subquotient of what's expected, which is 4D equals 4. And this just works out. And that just comes out as a nice computation of homological algebra. Just an odd parameter. Just each for odd normal direction. Yes, not parameters, but these are coming out of the sort of normal direction of it. And it's like if it's kind of not 4D equal 4, then you would have like less of them. 4D equal 1 has like even less of them. So 1, 2, 3. The number is coming out of having more supersymmetry. Yeah, I mean, this is the part that I was hiding about, like DV formalism. So I can say a little more later. Right. Another thing I didn't explain is this cross-string field theory. So what I claimed before was that what you assign to S1 is the space of closed string states. But physicists would say that this is coupled with the gravity theory, so it must be invariant under diffeomorphism. And in this topological setting, that just amounts to taking invariance under this S1 action. And mathematicians have also considered S1 invariance for different reasons, and that is what is known as a cyclic co-chains or cohomology, or chains or homology. They are sort of identified because things are Calabi-Yau. Anyway, the upshot is that when physicist friends say cross-string field theory, you may think of this cyclic homology. And essentially, basically, the only example that I need for today's talk is this what was originally called Kodaira-Spencer gauge theory, introduced by DCOV, and sort of in general dimension introduced by Costello and Lee. By this procedure, you can obtain some description of field theory like this. So these are underlying sort of field theory. So you can obtain this by doing, again, some homological algebra. Maybe the last ingredient that I want to mention is how this coupling of closed string field theory and D-brain gauge theory kind of works out. And for this is something kind of the neurosymmetry kind of experts who consider pretty open. There's something called closed open map, and there is this map from this closed string field theory and this D-brain gauge theory. And this cyclic co-chains, like for a formal reason, does the kind of the capture deformation theory of such a thing. Yeah. So physicists would know that if you have closed string state, I mean, I don't know, some super gravity background, it will give a deformation of D-brain gauge theory. And that's precisely given by this map. I mean, it's not quite a map in the sort of sense. It's like L-infinity morphism, but still, like you can give a deformation of D-brain gauge theory, and that is captured by such a thing. And again, kind of in examples, you can concretely kind of identify such a map. Okay, So with this, I want to say what an S-duality means. It's actually pretty simple. At least in the case when you are given a Calabi Sleaford, there is this action of SL2Z on this space, which is again kind of version of closed string states, version of the space of closed string states, closed string field theory, and there is this action, and that is kind of compatible with the physics expectation. So the content is that like you just define it, but then there was an expectation, which is that it is compatible with the SL2G action on M theory, just having a torus. And you make sense of all these kind of ingredients, at least in some subsector. Make sense of T-duality, make sense of reduction, make sense of M theory, make sense of 2A, at least to some extent, and then check that this SL2G action does correspond to the usual kind of SL2G action on torus of M theory. And it's kind of simple. So, I mean, just having this 0, -1, 1, 1, 1, it just looks like this. If you are writing this manner, it just looks like this. The point is that it's, at least in this expression, writing down this action of S-duality is pretty simple. But the claim is that somehow having this simple action, you can try to do some things. So before getting there, let me just say a few words about the summary. S-duality is the duality. And S-duality can actually be constructed mathematically, at least on a part of string theory, after defining that part of string theory. And somehow, remember, like in the first part, if you remember the first part still, it was about geometry Langlands, and I claim it's about like 4D field theory. And these 4D theories are exactly somehow what are going to be understood as a D-brain gauge theory in the context of the latter half. So I want to understand duality between D-brain gauge theories, and that's going to give some new sort of conjectural statements between like Langlandsy kind of objects. So, but I want to think of that as a duality between deformations of D-brain gauge theories. And this closed open map does actually produce S-duality of deformation of D-brain gauge theories. So maybe we are going to see an example. We are going to think of this particular case of Calabi 5 category. And what I'm going to do is this picture. So this is closed string field theory. This is a deformation, the complex which governs deformations of certain subsector of 4D n equal 4 theory. S-duality is acting here. If you have given an element here, x by s, you are getting an element there, same space. But by thinking of closed open map, here you are giving a particular deformation. You are thinking of image of this closed open map after taking S0. That's also giving a deformation, different deformation. But because you believe in S-duality, they should be giving sort of equivalent theories. That's sort of the idea. I mean, that's like what PGC was to say as well, but like we just kind of codify such a thing and make a definition. So that's what I mean by this. So let me just say, quickly say a few words about the examples. The first examples are, if you think about somehow, this was in terms of polyvector fields. In particular, it has all the polynomials on like a C3. I mean, there are like infinitely many polynomials you can consider, right? And if you think of some polynomials, I mean, each polynomial, like whatever polynomial you consider, is going to give some duality statement. So there are a lot of things you can consider. Let me just go through some simplistic examples. One is this polynomial. The variables were written as a z, w1, w2. And these were, again, like these details, I don't think this was meant is all understood, comprehensible. But you can hopefully believe that whenever you choose something, it's going to give two different deformations, just like the format setup that I made. And these two deformations are exactly corresponding to like this B model with the target fixed moduli, B model with the target like drum frequency and flat tree. And somehow, before deformation, I had what is called the Dolbeau geometry Langlands correspondence, which is also called the classical limit of geometry Langlands correspondence. And after this particular deformation, you get the usual geometry Langlands, the best of conjecture. And from this perspective, you can also obtain what is called the quantum geometry Langlands correspondence in a much simpler way than the, let's say, Kapustin and Witten kind of this. So it can recover from physics perspective the known mathematical conjectures in a sort of simpler way. The next example, you think of a particular configuration of branes. Don't think I have time. Yeah, this deformation gives a two different way of obtaining the Yangian. Yeah, that's I think it's explained in a work of like a Kosera and Yagi. Some part of it, I guess, I don't know. Another example, we just write down some particular information once again. Another degree 2 polynomial. And you just write down what these deformations are, the resulting guy is, and you compute one deformation gives a 4-dimensional Chern-Simons theory with a supergroup. But category of line defects of such theory is like kind of well known by now. It has to do with the representation theory of Yangian quantum affine algebras or unit quantum groups. On the other hand, deformation on the other in the other direction, that's particular deformation of the coherent difference fixed moduli. So it's certain difference module categories. And then yeah, you can just kind of immediately kind of guess that this line operators acting on the category boundary conditions of this theory. And that's, I mean, it's a meta conjecture because making this kind of a concrete actual mathematical conjecture takes some work. But you can see there is some relation between super Yangian and this deformation of fixed moduli from this perspective. And this was just like a third case, and you can imagine to do basically all sorts of things. Okay, for summary, QFT has been pretty useful in many ways, and Kapustin and Witten made a proposal on the relationship between geometry Langlands and quantum field theory, and somehow it didn't quite capture the algebraic dependence of your sort of space-time, but a mathematical framework can be developed for that. And once the framework is developed, then it can be used to do some other thing, just like any other thing. But then string theory and duality, a framework for those things can also be developed, and it is being developed. And that is also expected to give some interesting results. Okay, thank you.
Well, thanks, Professor Philsang, for the great talk. And are there any questions?
So I have a question. When you explained about the how to derive the geometric Langlands from using SGLity, right? And you said you can obtain the statements easily, but then I remember you explained at around the beginning that this is known to be false.
All right. So
right, what goes wrong?
Sorry. When you say what goes wrong, like which part are you?
Is this the best hope version of?
That's right. So I mean, I'm just like not explaining that part at all. So somehow, what this is saying is that you are expected to get equivalence between this theory and this theory. But you know, when you say two theories are equivalent, you need to get invariance in the right way and then compare. Right. Somehow the framework of physics so far have been great at kind of extracting numbers and equations, but not quite a category. So you need to extract categories in the right way, in the ways of the I developed interface. And then you'd expect to obtain that modified version.
Right. Oh, you get the modified version.
Right.
which
I
is
mean, I was
the
just
correct
like,
version.
didn't quite explain it here. Yeah.
And then this is still under development. I mean,
Which one?
this doesn't give you a proof, right?
I mean,
Yet.
absolutely not. I mean, it's just kind of giving a conjecture.
Ah,
So it's
okay.
sort of a statement, and you need to just prove. I mean, essentially, I'm just kind of making a definition of string theory, and then kind of understand sector of such things, and then kind of obtain kind of what is expected out of those, and that has nothing to do with actual mathematical proof of such a thing, kind of the consequence.
But which part of this picture is still a conjecture? The SGLE?
I don't know what to say. So I mean,
Right.
I mean,
thought
like,
you
SQLT is
actually
just, in a sense, like a definition. Like mathematically speaking, for us, this is a definition. So it's not even a conjecture. Like I don't know. Maybe conjecture, it's kind of you can make a meta conjecture if this definition of SQLT is a correct one. That would be a meta conjecture, but it doesn't have like a mathematical meaning.
All right, I'm still confused, so I'll ask you later.
Yeah.
Any other question? Okay, so if no, let's speak again.